All right, welcome back. We are learning about Bernoulli's equation, and we are going to apply it to calculating how long it will take to drain a pool using a hose. So we have our pool here. We have a hill, we have a hose, we have the exit of the hose below the entrance of the hose, which is necessary for the fluid to drain out. And we want to know what is the time it takes to drain. And we need a tool, right? We need a model that relates flow rates and heights. And the only thing we have that does that right now, because the only thing we have that doesn't deal with stationary fluids, is Bernoulli's. So we're definitely going to have to use Bernoulli's. So let's write down our Bernoulli's equation, which is P over rho plus 1/2 V squared plus GZ is equal to a constant. Great. For the record, what this also means, if this is equal to a constant, then we can say that anywhere along the streamline, because remember we derive Bernoulli's along a streamline. Anywhere along that streamline, these three things, when added together, are equal to a constant. So P at 0.1 divided by rho plus 1/2 V1 squared plus GZ1, so this is the properties at 0.1, anywhere on that streamline, have to be equal to a constant, which are equal to the pressure at 0.2 divided by rho plus 1/2 V2 squared plus GZ2. And the important part is these two sums of the are equal to a constant and equal to each other, although the proportions of these things can vary. So at one point you might have a lot of pressure and no velocity and no height. And then at 0.2, you might have a lot of velocity, right? And this would correspond to maybe air inside of a balloon that you're letting out, right? Inside of the balloon at the streamline, you'll have high pressure. Outside of the balloon, just outside the exit, you'll have a lot of velocity, but very little pressure. Right? And in both cases, we'll have zero height because with air, it doesn't matter a whole lot on the length scale of a balloon. If we're looking at the length scale of a building, a tall building, then yeah, it would matter. And then we're also going to need what we call conservation of mass. So with conservation of mass, we know that Q dot 1 is equal to Q dot 2, which is equal to, oops, not squared, 2. So this is equal to velocity times area. So flow rate, right, which is what Q is the volume per second of flow. So what this is basically saying is if we lose a certain volume per second in our pool, that means that volume per second has to be flowing out of our hose at the bottom. Pretty obvious, right? The non-obvious part is that we can calculate that by multiplying the average velocity times the cross-sectional area of both, right? So the velocity times the cross-sectional area of 0.1 has to be equal to the velocity times the cross-sectional area of 0.2, and that's called conservation of mass. V1 times A1 is equal to V2 times A2, right? Cool. All right. So step one with Bernoulli's problems is to always, always, always draw your streamline. So we're going to start at the top of our pool. And the reason why we're starting at the top of our pool is you always want to start and end your streamline in places where you know as much information as possible. Here, we know the pressure is atmospheric pressure, and we have a trick, which I'm going to show you here in a little bit, that also makes this very easy, right? And then our exit, we're going to choose just outside of our hose, and we're going to draw our streamline. We always, always, always draw our streamline, and the reason we always, always, always draw our streamline is because if we don't do that, we tend to make mistakes on the exam, and then we get lower grades than we want. And honestly, if you're making mistakes, that means you need to adjust your process, right? Because as engineers, we can't really afford to make mistakes. 1 to 2. All right, so we label the start and end, and we're going to now relate 0.1 and 0.2 using Bernoulli's equation, okay? Cool. So let's write our Bernoulli's equation out here from point 1 to point 2. So we have 1, oops, let's use our blue, 1 to equation 3. And our equation 3 is going to have P1 divided by rho plus 1/2 V1 squared plus GZ1 is equal to P2 divided by rho plus 1/2 V2 squared plus GZ2. Now, the trick with Bernoulli's is always going to be substituting in the things you know into Bernoulli's and changing the variables into variables that help you solve our problem, right? So at point 1, nowhere in the problem does it say we cannot use gauge pressure. So we're going to use gauge pressure. Let's write down our assumptions here, by the way. Assume, the first thing we're going to assume is gauge pressure, right? And that allows us to make that 0 and actually P2 0. We're going to label those A and A. And the reason we're labeling it A is because they're both at atmospheric pressure, so they have to be 0. Now, in order to use Bernoulli's, we also have a couple other assumptions we need to write out, which is that rho is equal to a constant. We have steady flow. And it is inviscid. We only have one fluid really, so we don't have to worry about the flow of through a streamline because it's also taken care of by steady state and rho is equal to a constant. But we can write it down if you guys want to. So we're going to do that. Flow along streamline. Cool. All right. So now we have a bunch of variables. We have Z1, we have Z2, we have V1, and we have V2. We have 4 variables. We're going to make we actually know Y1 and Y2, right? So we know our heights. So we actually know Z1 and Z2, which is great. But we still have 2 unknowns, 2 variables, which is V1 and V2. So we need to relate those together. And the way we're going to do that is through our conservation of mass equation. So we know that V1A1 is equal to V2A2. So we're going to say equation 2 to equation 4 gives us that V1A1 is equal to V2A2. And equation 4 to equation 5 tells us that V1 is equal to V2 times A2 over A1. Cool. Great. So we have now a relationship between V1 and V2, so we can plug that into our equation. So we're going to do 3 plus 5 into equation 6. Into equation 6, and we end up getting that 1/2 times this quantity squared here, which would be V2A2 over A1 squared, plus GZ1 is equal to 1/2 V2 squared plus GZ2. So we can now solve for V2, right? In fact, that's our goal, because if we know V2, we know the velocity of the height of our pool, and we can solve for when that velocity is, or when the height of the pool equals 0, knowing its velocity. So let's try to do that. We're going to solve for our velocity. So if we do that, we get that, let's do 6 to 7. Oops, didn't draw that very well, sorry. We get that Z1 minus Z2 is equal to 1/2 V2 squared times 1 minus A1 over A2 squared. And if we want to solve for V2, we get that now 7 to 8. V2 is equal to 2G times Z1 minus Z2 all over 1 minus A2 minus A1 squared. And this is all to the 1/2 power. So if we write this out, we get, if we plug in numbers, 2 times 9.8 meters per second squared times 3 meters divided by 1 minus 0.01 meters squared, which is the area of the tube. That's D2 divided by, oh, we got to square the whole thing actually, because that's the diameter. So squared divided by 10 meters squared. And now normally if we're trying to find these areas, right, we would multiply the areas by, it's pi d squared divided by 4, but we're dividing by pi d squared divided by 4. So the pi's and the 4's cancel out and all we're left with is the d squared. So if we're just doing a ratio of areas of circles, we can just use the d squared. So that's exactly what we're doing here. 0.01 meters squared divided by 10 meters squared. And all of this is to the 1/2 power. And if we solve for it, we end up getting that V2 is equal to 7.6 meters per second. Fantastic. And all that means is that now if we want to figure out what V1 is, we solve for that by now plugging that into our conservation of mass equation. So we say equation 9, let's just say equation 9, we get that 1 meter divided by the 10 meters squared divided by, I did this wrong, my bad. Equation 9 is V1 is equal to 7.8 meters per second times 0.1 meters, 0.01 meters squared divided by 10 meters squared, which gives us that V1 is equal to 7.8 times 10 to the 6th meters per second, which is really slow. Your width of your hair is about 100 microns, and this is going at 7 microns per second. So it would take about 10 seconds for it to fall the width of your hair, which is pretty crazy. So we look at a total time. Total time is just going to be distance divided by velocity. So 1 meter depth of a pool divided by our V1 is equal to 1 meter divided by 7.8 times 10 to the negative 6 meters per second equals 0.13 times 10 to the 6th seconds, which is actually 36.2 hours. Which is good to know that if you travel at about 1 hair every 10 seconds, 1 hair width every 10 seconds, you'll go a meter in about a day and a half. That's really slow. So it'll take about a day and a half to empty our pool, right? Interesting. So here's a question for you though. If you had to place a bet, would it take longer or shorter amount of time? Would the actual pool take a longer or shorter amount of time? Based on the work we did here, right? And thinking about what we neglected and what will actually happen in real life and be important. So I want you to pause, think about it, and then actually circle one of these and take a stand and feel some pride about what you did. In other words, think about it long enough that you think you're going to be right, or at least have a chance. Okay, you pause. I'm going to come back. All right, I'm back. So if I had to place a bet, I would say that it would actually take longer amount of time for the pool to empty. And the reason why I think this is because Bernoulli's, there's 2 reasons actually. Bernoulli's, the first is Bernoulli's neglects, can you finish this for me? Viscous effects. The pipe is relatively small, right? It's a garden hose. Remember we said that with shear stress, tau is equal to mu du dy. So if we increase our velocity, sorry, if we want to make tau small, we have to decrease our velocity or increase our area, but the converse is also true. If we have a small distance will cause our shear stress to rise up. So a hose, which is only less than an inch across, it's going to have some viscous losses in it, right? Which means that it's going to slow down our flow. Yeah, so if we neglect it, then our flow is going to be smaller, which means that our pool will take longer to drain. And the reason is, if we go back up here, we can talk about Bernoulli's as a conservation of energy equation. We have a pressure energy plus a kinetic energy plus a potential energy is equal to a pressure energy plus a kinetic energy plus a potential, like gravitational potential energy. And these things can exchange between one another, but that assumes a perfect world with no viscous losses. That means if we have a whole bunch of pressure energy, we can change it into velocity, pure kinetic energy. In reality, some of that is going to go whoop into heat, right? So the more viscous losses we have, the more energy gets lost into heat, and the less can go into our velocity at the end, which means our overall velocity is less, which means our flow rate is less, which means our pool takes longer to drain. Cool, so that's reason one. Reason number two was right here. We just solved for V2 and then plugged it in and assumed that the velocity of the pool was going to be a constant. It turns out it's not going to be a constant. Z1, the height of the pool, is not going to stay constant, right? It's falling as it goes. So the potential energy that we have available, the gravitational potential energy we have available at point one is going to decrease with time, which means our velocity at the exit is going to decrease with time. And what we could have done is we could have said that Z1 is equal to H, all right? We could have said that V1 is equal to DH dt. And we could have solved for V1 and plugged that in and gotten a differential equation and solved the differential equation and solved for the height as a function of time. And in fact, we're going to do that in one of the future problems here in a little bit. But the end result is that at later times, when the pool has drained a bit, our height is going to be less. We're going to have less potential energy. We're going to have less kinetic energy at the end, which means less velocity, which means it's going to take longer for a pool to drain. So all in all, 36 hours seems like a long time, but it will likely take the pool much longer than that to drain. In other words, this is not a very conservative model, right? A conservative model usually means that it overestimates whatever quantity you're trying to estimate, right? Now, what does over mean? Over just usually means that it is wrong in a direction that is least harmful to you, right? So let's say you want to disassemble this pool because you're trying to drain it and you want to get rid of it. And you start draining it on a Wednesday or Thursday, and you have a bunch of friends coming over on Saturday to disassemble the pool with you. And you're like, well, I calculated it. It'll take 36.2 hours to drain. It will be drained by the time they get here Saturday morning, right? But you're wrong. It will take much longer than 36.2 hours. So it's not done draining by the time your friends get here on Saturday morning. They sit around waiting, probably drinking a beer or two. And before noon, that's usually not a great idea, right? Well, never mind. You guys aren't 40. You're not going to get headaches like I do. But anyway, the point is, you wanted the pool to drain before your friends got here. So a conservative estimate would have overestimated the amount of time that a conservative model would have overestimated the amount of time that it would have taken to drain the pool, because then you would have known you would have been right. You might have been waiting longer than you wanted to, but at least you wouldn't have wasted your friend's time, right? So we're going to talk a lot about what a conservative model means as the semester goes on, and whether or not the models we're using are conservative or not. Here, I would say this is not a conservative model, because I would want to know for sure that the pool is drained when that time is up. And here, we already know that it's not going to be drained at 36.2 hours. Cool. All right, so our next problem, we don't have a next video. we're going to talk about our semester-long design problem in class, and then after this, we're going to do a bunch of Bernoulli's example problems that are kind of fun. So, all right, I'll see you in the next video.